Well, I'm going to show your domain diffusion guidance for 3D CBCT MA paper presentation. I'm Yongjin Choi from Korea University. CBCT is widely utilized in dental diagnosis and treatment procedures, including dental implant placement, orthodontic appliances, and orthodontic surgery. CBCT restores into 3D from the projection images that can by rotating around the head using algorithms like FDK. The presence of metallic inserts such as dental crowns, implants, can result in artifacts during CBCT imaging. These artifacts can obscure dental and oral structures, complicating the three-dimensional volumetric reconstruction and hindering accurate diagnosis. In particular, the intractable nature of artifact structures complicates mathematical modeling, thereby making their removal a challenging process. So, we aim to remove metal artifacts in CBCT through 3D metal artifact reduction. We think of the metal-affected CBCT as clean CBCT with added metal artifacts. So in order to obtain clean CBCT, we aim to separate the metal artifacts X0M and clean CBCT X0 star from metal-affected CBCT X0. We use two 2D conditional diffusion models, each modeling clean CBCT slice and metal artifact slice. Then the posterior distribution at time t is as follows. During training, each diffusion model uses denoising score matching losses. In here, to obtain metal artifact data from training the diffusion model, we segmented a random number of teeth from the clean CBCT and inserted synthetic metal inserts into the segmented teeth to create metal affected CBCT and use the residual obtained by the subtracting the clean CBCT. However, the 3D MAF problem cannot be effectively solved using only the 2D diffusion model. Therefore, we use 3D cone-beam geometry to effectively input constraints on 3D. Since cone-beam projection uses images projected from the side views, it can consider the correlation between the z-axis. And here, Y is the 3D cone-beam projection, A is the projection operation, and N is the Gaussian noise, but we don't consider the Gaussian noise. Then the posterior distribution given Y is defined as follows. And since Y is determined by X0, Y can be ignored. By using the base rule and modeling X0 star and X0 M using independent diffusion models, we get the following equation. And this is our first main contribution. We independently update the metal-free CBCT and metal artifact diffusion model using their respective denoising scores. And this is the gradient of the log likelihood term used for the updates. Here, alpha1, beta1, and alpha2. Beta2 is the hyperparameter for each guidance. But log P of X0 given XT star and XTN, and log P Y given XT star and XTN is intractable. So we use diffusion posterior sampling to approximate the guidance term. According to diffusion posterior sampling, we can substitute XT star and XTM with the posterior mean X0 star hat and X0 M hat, which approximate to X0 star and X0 M. However, diffusion posterior sampling requires backpropagation of the diffusion model at every gradient step during the cone-beam projection guidance process, which requires too much memory usage. If there are 256 CBCT slices, 512 computational graphs for the two diffusion models must be simultaneously loaded into the memory. Therefore, we hijack the DTPS update path to take the gradient step with respect to X0 star hat and X0 M hat not the XT star and XTM. Intuitively, before taking the reverse diffusion step for XT star and XTM, we can update the posterior mean via guidance to make it closer to X0, and then take the reverse diffusion step. And this is our second main contribution. We collected 48 clean CBCT volumes and made synthetic matter artifacts. And we used 23 volumes for training and remaining 25 volumes for testing. And also we tested on 3 volumes of clinical matter affected CBCT volumes. And for generalization, from the work of Choi, we acquired 6 CBCT volumes from different imaging equipment, projection geometry, and resolution, and we used these data as out-of-distribution dataset. And here is the synthetic data type results compared to 2D and 3D MAR baselines in DidoNet Plus, ACDNet, and FEL. Our model performs in all 3 planes. In the blind DPS, which uses the 2D diffusion models for inverse problem solving, performance drops in the coronal and sagittal planes so much, but ours performs well in all 3 planes. And similar results, good results are also seen in visualization. While the existing CNN-based approaches smooth the region around the meta artifacts, ours well restores the region based on the strong diffusion prior. And this is the out-of-distribution results. Existing 2D-based MARs, such as DidoNet Plus and ACDNet, are not bad in quantitative results, but when looking at the visualized results, we can see that generalization is not well done, and FEL, blind DPS, are not good either numerically or visually. On the other hand, ours is superior both numerically and visually compared to the baseline models. And lastly, this is our clinical results. Despite being trained on synthetic dataset, we can visually see that the meta artifacts reduction works well on actual clinical data. In conclusion, we proposed a dual domain guided diffusion model for 3D meta artifact reduction, and we showed memory efficient diffusion posterior sampling step for 3D medical imaging. Thank you.